Hello there, welcome to session 6 of Unit 3. And in this section, we'll be looking at thermal conductivity. Let's look at the objectives of this section. We have two objectives here, and the first objective is to be able to define thermal conductivity of a material. Secondly, derive equation for the conduction rate of heat through a single slab and composite slabs. Have you observed that anytime that you are cooking and you leave a metal spoon in the soup or stew or anything that you have on fire, with time the handle of the spoon, or let's say the handle, becomes hot. This is due to the process we call the thermal conductivity. We can define thermal conductivity as the ability of a substance to conduct heat. In this process, the transfer can be represented on the atomic scale level as the exchange of kinetic energy between the microscopic particles. Example of this microscopic particle is the molecule atom of free electrons. The vibrational amplitude of the atoms or the electrons of the metal at the fire end of the spoon becomes relatively large because of high temperature of the environment. This increases the vibrational amplitude, and the association of energy are passed along the spoon from one atom to another atom through collision between the adjacent atoms. So with time, the handle of the spoon's temperature becomes very hot. With experiments, or with a series of experiments, have shown that the conduction rate or the rate of heat flow at P can be given as this expression. Thus, P equals Q over T equals Ka Th minus Tc over L, where our L here is the length between the warm body and the colder body. Our T here is the change in temperature, that's for the hot and that's for the cold. And we have our area as a cross-sectional area where the heat is flowing through. And our K here is the thermal conductivity. And we have our P here to be to be power, and Q here as the energy and time. So with this relation, you can actually calculate for everything here, or say the thermal conductivity when made the subject. Now let's look at conduction through a composite slab. In the figure shown here, a composite slab consisting of two materials having different thickness, say L1 and L2, and different thermal conductivity, say K1 and K2. The temperature of the outer surface of the slab are Th, that's for the hot reservoir, and Tc, that's for the cold reservoir. And each surface of the slab too has an area called we can term as A. From here, we can find the rate of heat flow P for slab 1 and for slab 2. And in combining them, we will get the rate change of P to be equal to A into bracket Th minus Tc, all divided by L1 over K1 plus L2 over K2. But supposing that we have a particular number or more than two number of slabs, meaning we can use this formula in calculating for our P or for our K, so that A will be in the bracket T, we get A multiplying Th, that's our hot reservoir, minus Tc, all divided by the summation of L, that is the length, divided by K. Let's look at the thermal conductivity of some substances. Substances like metals, or say gases. Metals like stainless steel, lead, iron, brass, aluminum, copper, and silver has a thermal conductivity of 14, 35, 67, 109, 235, 401, and 428 respectively. Unless we have a material that has not been existed yet or discovered yet, we will not have the thermal conductivity. But all metals has its thermal conductivity. And I think when you check online, you see all.